Welcome to the Oxford Discrete Maths and Probability seminar. So as usual, everyone's muted, but we encourage you to ask questions in the chat, and then Christina and I will curate them and we'll interrupt Julian if we think something needs asking immediately, otherwise questions at the end. So it's a great pleasure to have Julian Sahasrabudhe to talk on combinatorics from the roots of polynomials.
Great. Thank you very much, Alex. And thanks for having me. This has been a really wonderful seminar. I'm glad you pulled it together in such short notice. I've been lapping it up. And happy to give back when I can. All right, so today's right. So I'm talking about really a favorite topic of mine, which is I hope I will convince you is surprising. And in fact, I really got interested in this specific set of conjectures because I thought they were ridiculous. They were far too good to be true. But on the other hand, I got sucked in, as we'll see. And I'll try to convince you that the results are quite surprising. Okay, so I'll be talking about joint work today with my collaborator, Marcus Michelen, and he's another young researcher at University of Illinois at Chicago. All right, so what am I talking about? So throughout this talk, I'm going to have X a random variable. And for what essentially always, this will be taking values between 0 and n. Okay, so I always get a question in the talk, oh, well, what about other kinds of values? What if it's real values and so on? Answer is you can generalize, but I think it's enough to think for now, positive integer values. And we can talk about generalizations later. So positive integer values. And with this random variable, so this is just any random variable, any distribution, I can associate the probability generating function. I can build this polynomial f of x. And so just a polynomial where the ith coefficient is, or the kth coefficient, and just the probability x is equal to k. Right, so just some positive polynomial with non-negative coefficients. And the really interesting question to me, so I'm going to start at very big picture right now. So the interesting question is, okay, this is a polynomial. It has n roots flying around in the complex plane, sitting in the complex plane. If I know something about those roots, can I say something about the distribution? If I know something about the distribution, can I say something about the roots? Is there some relationship between these two sides of this picture here? Okay. So I'm going to start out with really a first example, and you'll see from this date, 67, it's not too recent. And we'll see, and I'll actually prove this theorem, and we'll see, okay, actually it's quite basic, but then it will start getting us to more heavier things. All right, so let's start about a first connection between the distribution of x and the roots. Okay, so I'm going to let xn be, I'm going to use this notation here to mean is a random variable taking values in 0 to n, right? It's a bit dirty, but it's clear. And I'm going to assume that the standard deviation of this sequence of random variables tends to infinity. Okay, so they're fluctuating. Great. Now, here comes my assumption about the roots, because I'm interested between the roots and the distribution. Let's make a very strong assumption. Let's assume that all the roots are in fact real. So a very, very strong assumption. What can we say about xn? And Harper's theorem says that if I appropriately center this, so I'm just going to subtract the mean here, and then I divide by the standard deviation, this very familiar fraction, this will tend to a normal distribution with variance 1. And this is in distribution as n tends to infinity. So this is already, okay, I stress this is a very strong situation because this real rooted hypothesis, as we'll see, is one hell of a strong assumption. But already we see, this is very interesting like distributional behavior based on nothing other than the locational of the roots. Okay, and some non-triviality condition about the standard deviation. If the standard deviation doesn't go to infinity, there's actually no way it could be normal because this is a discrete distribution, and this thing will stay discrete. Okay, so this will be a hypothesis throughout the talk. Okay, so I'm going to just jump in and sketch a proof of this. It's not hard, and we'll see after unfolding it a little bit what's going on, but that will lead us to some more interesting things. So let's try to prove this. All right, so we get our xn's and we have our cool fn polynomials. All right, and for now, I'm just going to assume that the degree of fn is equal to n. This is just some stupid sequentiality issue, right? Because I could just relabel things to ensure this holds. So it doesn't matter. Okay, now we have our cool function, and we know that all the roots are real, so let's factor this thing out. Okay. And we have the happy news that these zetas here are real. And secondly, and so here comes an observation, that they're actually all negative. And so why are they all negative, right? Well, this is just because all the coefficients of this f are positive or non-negative. So every time I put a positive value into that function, I'm going to get a positive number. So it can't be a root, for example. So all of these guys have to be non-positive. So this minus zeta, that thing is positive. Okay, this will be important in a second. All right, so now I'm going to rewrite this thing again, just sort of renormalize this fraction. So all I've done is divide by this 1 minus zeta I in every coordinate. And you notice here that the c disappeared. And if you think hard about what the c has to be, it means it will exactly cancel with this factorization. So that's good. This looks like a nice happy form. I should say, please do ask questions. I'm very flexible with the talk, and I'm happy to linger on things if people are or go in other directions if people want to. Okay, so now we have this nice happy form, and let me just point out two things to start. First of all, this thing here is a positive number. So this minus zeta is positive, and this 1 minus zeta is also positive, right? So this is plus a positive number. Likewise, this is a positive number here. And we might realize, and another important observation is that these two numbers, this thing plus this thing, sum to 1. So let me just rewrite this like this, grouping my positive guys together. And you'll notice that each of these terms is actually the probability distribution function of a Bernoulli random variable, right? So what was a probability distribution function? It was just the coefficient, which is the number, times the probability you take that. So you take 1 with probability 1 over 1 minus zeta I, great. So z times 1 over zeta I, and then 0 with this probability. So the 0th coefficient is this guy here. Okay. So now we've noticed this amazing coincidence that f is written as a sum of a product of Bernoullis. And then wait a second, what does that mean? So here's another, again, this is nothing. I'm just unraveling the definitions of what's going on here. So, although I guess you could say that about all mathematics in some sense, but okay. I'm unraveling the definition of what's happening here. Right, so f of x, right, if it factors, if I'm in this happy situation, when I factor as the probability generating functions of a y and of a z, that actually means something very special. It means that x is equal to y plus z, where y and z are independent. So it's this very happy situation. And we're in a very, very happy situation because we've written as this big product of all of these Bernoullis. So the conclusion is that X is actually a product of the sum of Bernoullis, of independent Bernoullis. Okay, so this is an old friend and we know quite a bit about it, right? So if we additionally have that the standard deviation of this, so this is really a sequence of X's here. And this will give me, for every X, I get some factorization of these guys. But if my standard deviation is large, we know that this X is approximately normal. And in particular, if I center it properly, scale it properly, this thing is going to be normal. By the central limit theorem, I should say. I mean, this is actually even so strong, we could even use Barry-Yassine or something to give an immediately give an effective difference. Okay. Are there any questions about this proof, actually? I know this is not a call and response kind of talk. Okay. So what have we proved? We proved Harper's theorems, which says this, that if we have that all the roots are real, then we have this central limit theorem-like behavior. And the proof is basically, it was really just the central limit theorem, but in disguise, when I sort of open it up a little bit. But with this question comes, with this basic theorem comes a really interesting question, which is, what is the correct condition on the roots to guarantee normal behavior? Wow, the sun is right in my eyes. I wasn't expecting that. So we know we had under this condition of real rootedness, we got it, but real rootedness is very strong. So what's the correct condition that will give us normal behavior? But before I want to jump into this question, I want to say that Harper's theorem is already in itself pretty interesting, and it leads to some interesting results. So I thought I'd just mention this old theorem and lovely theorem of Godsil from the 80s. And I should say this also gives some flavor for the kind of distributions. Okay, so you might ask, like, okay, great. If you can say something about, the roots, about the distribution from the roots, who cares? What if you never know anything about the roots? But there really are these amazing situations where the random variable itself is very mysterious, but yet you can say something really strong about its roots. And that's really what this is about. So let's look at this old example of Godsil, this very pretty result. So if I take a d-regular graph on n vertices, and n I'm going to imagine to be very large here. And what I'm going to do is I'm going to select a random matching from G uniformly among all matchings. So this is not a perfect matching. This is just some collection of edges, that have no vertex in common. And then I ask, how large is this matching? So that's my random variable. This theorem of Godsil says that random variable has normal behavior. So the size of a randomly drawn matching is approximately normal. This is in a d-regular graph on n vertices. So I think you should be, if you don't know this theorem already, I think it's definitely a surprising theorem that you could be able to say something so strong about what is actually quite an elusive random variable in some ways. And the road into proving this theorem, and indeed how Godsil proves it, is he first uses this extremely interesting, again quite old, theorem of Heinemann and Lieb, which says that the roots of this characteristic polynomial, right? So this is just the same thing, but now I do it for matchings. What's the probability I get a matching of size k, a matching of size k plus, so on. The roots of this thing are real. And then secondly, you need to show that the variance is large. It turns out this is also a consequence of Heinemann and Lieb. It also gives you some bounds on the location of the roots, which then implies this condition. And then all of a sudden you can just apply this Harper's theorem, and then you're done. So this is an early example of how you can get a handle of this quite crazy distribution via the root distribution. And I should say this is, you know, this was done in the 80s and it's certainly not gone forgotten. And a more modern reference is this work of Jeff Kahn from 2000, where he really nails down what the right condition is. So goes far beyond deregular and dives quite a bit deeper. But I should say, even in this work, and there's a lot more combinatorial work in this, you still need to use Heinemann-Lieb theorem plus Harper. You need to go through zeros to get that final result about the central limit theorems. So, and going further says, okay, we need our central limit theorem from some other kind of theorem. Okay, so now let's bring back to this central question for us today. What is the correct condition in Harper's theorem to guarantee normal behavior on the roots? And there's this condition. And honestly, the first place I've seen that has any sort of idea of how to approach even heuristically this question or heard of is this really interesting heuristic that I learned, that comes from Pemantle, who considered the following thing. So he went back to this proof of Harper's theorem and said, okay, so we have this nice form, right? But there wasn't anything special about the roots being real at this point. I'm happy to normalize this. I'm happy to write any polynomial in this form. I mean, in fact, the C disappears. That's something just a consequence of the fact that this is a probability generating function. Okay, so I'm happy to write my polynomial in this form with the caveat, now these are not happy real numbers that are these guys positive, but these are just some crazy complex numbers. But he said, okay, fine. Say that's not a problem, that's not a problem. We're thinking heuristically here. What's the problem in this sort of that is suggested by this object, right? The problem is suggested by if one of these zetas is too close to 1. Right? And it's making one of these factors contribute too much to this big product. And this sort of makes a lot of sense, because if you think about the central limit theorem, or at least how I think about the central limit theorem, what does it say? It says, if I have a bunch of random variables, this is more general, so I just have a bunch of random variables. If none of those guys are sort of jumping up and, if they're independent, importantly, and none of them are jumping up and contributing too much, then I should have normal behavior. And Pemantle's heuristic says, well, let's imagine this holds more generally for these some crazy polynomials. So this is some sort of more general sort of convolution or something of measures, or complex measures, say. Maybe something similar is true. All you need is that this zeta is not getting too close to 1, and none of these terms are not blowing up too much. Okay, so that sort of parallels maybe the heuristic understanding of a central limit theorem. Okay, so in a bit more concretely, let's write out this conjecture of Pemantle's. So he conjectured that let's fix a delta and say I have a sequence of random variables where the standard deviation tends to infinity, right? So this is I always need standard deviation tends to infinity. Now let's just assume that all my roots are just bounded away from 1, right, by some delta. Then he conjectures we have a central limit theorem in this case. I'm just gonna actually close the blind, it's right in my face. All right. That didn't quite do it. And that's not a problem I expected to be having. I admit. Okay, so Right, so this is the conjecture of Pemantle, and I'd now like to sort of phrase a bunch of work that's been that contributes towards Pemantle, but we'll see like some of these results are actually quite a bit older than the conjecture themselves. So I'm trying to arrange the previously known literature around this conjecture, which is sort of yeah, the natural thing. Okay, so. A similar result, so some sort of result of this form was proved by Igolnitzer and Souliard in the context of the Ising model. So they were looking in specifically at some sort of distributions connected to the Ising model. So looking at the appropriate partition function and so on. And they are able to prove something in this case. And if you look at this paper, they really need this implicit assumption that the standard deviation is growing much faster, is like n to the 1/3. So in their context, they actually get it for free from some other considerations, but this is sort of implicit in their work there. Okay. Another really interesting result in this direction is due to Huang and Zaharovas, who proved Pemantle's conjecture is true if all the roots are on the unit circle. So again, this is a much stronger condition than in Pemantle's situation. And I should say that Huang and Zaharovas actually proved much more than just this. So they are able to classify the different types of measures that are available when you're in this interesting situation with all the roots on the unit circle. But one of the consequences of their work is that they're able to prove Pemantle's conjecture follows from their work in this case. And a really key reference here is that of Leibowitz, Pittel, Ruel, and Speer, who managed to prove a version of, well, actually before Pemantle conjecture, proved a version of Pemantle's conjecture explicitly if the variance is growing fast enough, if the standard deviation is growing fast enough. Of course, it's the same thing up to power 2, right? And this n to the 1/3 here is no mistake. And in fact, all of these results, in a sense, are hitting this same n to the 1/3 barrier. Here it's just invisible because we, again, always have the variance is big enough in this situation. That's an interesting observation of the work of Huang and Zaharovas, is that you always have big variance on the unit circle. So there seems to be a real barrier here. And indeed, this is the case because we can show that if to go below n to the 1/3, you need some more information about the polynomial. And in particular, you need the information that the coefficients are positive. So if it is indeed true that anything like Pemantle's conjecture is true, that you just need this basic condition on the variance, then there's a much more subtle interplay between the positivity of the coefficients, right? Every probability is greater than or equal to 0, and the distribution of the roots. So there's a more subtle interplay. If n is bigger than 1 to the 3rd here, that's sort of swept under the rug. And so Marcus and I introduced a new idea into this mix when we were able to push this below this sort of barrier and get the variance condition down just to any polynomial growth size. And in the same paper, we were, in some sense, unfortunately, able to prove that Pemantle's conjecture is actually false. So I would like to give a lot of credit to this, to Pemantle and this conjecture, because I think it's extremely interesting and extremely like visionary to see so far beyond these results and think that something like this might be true. And in a sense, as we'll see soon, that this was really the right question to ask. This was just a little bit greedy. So it was just a little bit too far. And we'll get into exactly what I mean by false in a second. Okay, so the first result I'd like to present to you today is a result of Marcus Michelen and myself that really nails down the truth in Pemantle's conjecture. So, and in fact, we're going to even step into a slightly simpler and harder setting. So instead of considering a sequence of random variables, I'm just going to fix a single random variable and look at its the total distance between that random variable and a normal distribution. Okay, so here we go. So you give me your random variable, anything you like, taking values between 0 and n. And now I'm just going to define this notation just to keep everything a bit more compact. Just center it and renormalize it appropriately. And now I'm going to write down the roots of this probability generating function. Okay, so it doesn't really matter. It might not actually have been degree n, but whatever. So I write down the roots of my probability generating function. And now I'm going to define delta p to this minimum distance. So I just look at all those roots. There's a bunch of them in the complex plane. Look at one in the complex plane and just measure that distance between the closest root and 1. And now what our main theorem gives here is a quantitative estimate on the distance between x, right? I don't know anything about x except for this delta, and the distribution of a normal random variable. So what is this saying for any t? So z is a normal random variable. So this thing here, for example, is just some number, right? It's this weird integral 0 to minus infinity to t, blah, blah, blah. This is just an integral. This is just a number. And now I'm comparing what the probability of my renormalized random variable is less than t to this normal. Okay. And this gives a bound that just depends on this minimum distance, the standard deviation, and n. Okay. Okay, so let me make a few remarks about what we're looking at here. So the first remark is that actually this result is sharp. So for example, this log n that appears here is the log n that Pemantle missed. So as I'll say it a bit more clearly in a second, but what this says is that he should have had the variance, the standard deviation, at least log n in his theorem. But this tells us actually quite a bit more. So this tells us not only for delta fixed, it tells us for any delta rate. So it just says if your standard deviation is growing faster than this closest root times log n, then like 1 over whatever, the closest root is beating this out, then this thing is tending to a normal. So we're really allowed delta to vary in this. And this is actually the correct dependence even when delta is varying. So it's tight in all 3 parameters here. Okay, so let's try to understand this by looking again at Pemantle's conjecture. So let's line it up to see exactly how this compares and what that says about his extremely interesting conjecture. Okay, so he had a sequence of random variables, and here was the naughty bit: is he had sigma n only sigma n tending to infinity. So I put it in red here. Okay, and if all the roots have distance at least this fixed delta away, they're avoiding some ball around 1, then we have this normal behavior. Our results say that Pemantle's conjecture is true, not with this highlighted bit, but if sigma n is greater than log n. And this is the truth. So this is the sharp bound. Maybe this is a good time to pause and ask for any questions, if there are anything appearing. So far, so good. All right, so now I'd actually like to take a bit of, okay, so I should say this is really resolving this original conjecture of Pemantle, and for example, gives the sharp form of this result of Leibowitz, Pittel, Ruel, and Speer, and resolves this first question that I set us up with, which is what is the correct, in some sense, what is the correct condition in Harper's theorem? So now I'd actually like to come at this question from a different direction. So I'm sort of we're gonna leave this at a bit of a loose end for a moment and jump off in some other direction. I see that there's a question in the chat, perhaps. Okay, so Thomas asks, by the truth, do you mean that the sigma is less than some constant times log, then the claim is not true? Yes, that's true. Yeah, so there exist examples which have standard deviation proportional to log n that don't tend to normal, and avoid a ball around the unit circle of size 1/10 or something. Yeah, thank you. Great. Great. Okay, so now I'm going to sort of jump off in another direction, and then we'll see we swerve back into this main trajectory of the proof eventually. All right, so this another perspective comes from another set of questions asked not about single random variables taking values between 0 and n, but multi-dimensional random variables, or if you like, joint distributions. Okay, so what am I talking about? I'm just imagining x takes values, for example, in some d-dimensional grid. Okay, and okay, so now we're in this cool multi-dimensional world. I'm going to need to tell you what the appropriate polynomial is for this multi-dimensional thing. And it's actually a very natural generalization, so let's write it down. Now, for each sort of coordinate in this grid, I define a monomial in the obvious way. So I1 up to ID, that coordinate in the grid. Now I look at the monomial Z1 to the I1, blah, 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 blah. Okay. And now what's my coefficient? Just the probability that I hit that lattice point in this grid. All right. Okay, so now the question becomes, what is the connection between really the roots of this guy and the roots of x? So in this situation, we're just going to consider polynomials of a very specific type. So here comes a definition. I'll say that f sub x, or a polynomial like this, is real stable if it has no roots in what's called the upper half plane. Okay, so this is kind of a crazy definition I'm throwing at you, but I'll try to say something why it's natural in a minute. Well, a very little bit about why it's natural in a minute. So it turns out this is actually a very well-studied notion. So, and okay, I'll say more in a second. Okay, so basically what this is real stable polynomials are polynomials that have no roots in some crazy set, right? Which is this sort of quadrant of the complex plane. All right. So let me give you an example of a real stable polynomial to try to convince you that these are natural objects. In fact, they're fantastically well-studied objects. So if I take a connected graph, vertices v, edges e, I'm now, for every edge in my graph, I'm going to define some variable z sub e. So every edge gets a variable. And I'm going to define this polynomial, which is, wait for it, the sum over all spanning trees in the graph And I'm going to product over all the edges in the spanning tree T. So this is sort of just writing down in this polynomially way all the spanning trees in my graph. Okay, so we heard a couple of weeks ago that spanning trees were magical objects in probability, the stars of improbability. And indeed, if you don't know this already, it should shock and horrify you that this polynomial is real stable. So, this can be proved, for example, via some matrix tree theorem. And okay, maybe you need quite a bit of the theory of real stable. Okay, maybe not too bad. Maybe not too bad. Okay, but okay, the point is that these sorts of polynomials really do exist, and they appear in these natural settings. And we're going to journey a little bit deeper into this, but again, I'm only going to wave my hands a little bit. So, okay, so here's sort of the starting point of the of this other tributary that will lead back into our mainstream today, which is this incredibly influential paper of Pemantle from 2000. And it's quite a cool, like, big picture paper. And in this paper, he's trying to figure out what is the correct notion for negatively dependent random variables. So I don't want to go into what he's talking about there, but I just want to appeal to you on a intuitive level. So by negatively dependent, I mean something like I have a bunch of random variables, and they're not independent, but rather they have some sort of negative dependence that sort of, if this one is large, then that's sort of pushing the others down in some appropriate way. And in this paper, he gives a bunch of combinatorial properties that he says would be desirable for the correct notion of negative dependence. So he doesn't know what the correct notion of negative dependence is, but he's trying to build a theory, and he's trying to say what the aspects of that theory should have. And a few years later, this really surprising paper comes along of Borsia, Brendan, and Liggett, where they actually give a definition that satisfies these criteria of Pemantle. And their definition is, quite amazingly, a collection of random variables is negatively dependent if their joint probability distribution has a real stable probability generating function. So let's write this craziness down. So these guys, I want these to be negatively dependent. This is some crazy word in the sense of Pemantle. If this generating function of this joint distribution is real stable, right? So this was this crazy definition saying that if you look at the roots of all this thing of this polynomial, it doesn't intersect some quadrant in the complex plane. So I think this is a really beautiful example of sort of connection between combinatorial and probabilistic ideas and zeros. And it's where another motivation for us picks up, because with this definition comes the question, aha, so this is a beautiful definition of what it means to be negatively dependent. What can we say about these distributions? So I just have a bunch of random variables, right? And this joint distribution is real stable. Can I say something about the large scale behavior of that distribution X? What does that thing look like at a big scale? So this is the second question that I'm interested in a vague form. So we'll nail it down a little bit more in a second. And to understand what this means, we need a little bit of notation. So if I have a joint distribution like this, taking values, this is a random variable, just taking values in R. The covariance matrix, okay, so this is obvious to probabilists, but I say it anyway. So the the covariance matrix is the D by D matrix, for which the ijth entry is just this covariance. Right? So I just put all the covariances into this matrix. And now we need to define a notion of the standard deviation, or the variance, and just define that to be the operator norm, the L2 operator norm of this matrix. Okay. This matrix is also positive semi-definite, as I've written here. And it turns out for every positive semi-definite matrix, there exists a normal distribution with exactly that covariance structure. This sounds a bit confusing, but in some sense it's obvious, right? So on the real line, there's essentially one normal distribution. I guess there is one normal distribution when you renormalize it. But in higher dimensions, now you can skew this distribution by a positive semi-definite matrix, or multiply it by a positive semi-definite matrix, and you get a slightly different covariance structure. Okay, so there's a whole family of these normal distributions in R to the n. And now we can put a bit more meat on the bones here. So I was interested in this question of what's the limit shape of these distributions. And a very particular question was laid out by Ghosh, Liggett, and Pemantle, where they conjectured actually that the limit shape should be a multidimensional normal. So if you look, so if we fix D and we look at a sequence of these random variables, if we assume that the probability generating function of this joint thing is real stable, then, and we always need that the maximum variance is tending to infinity, right? This is that the scale is going to infinity. Then this fraction, our favorite fraction, the recentered and renormalized things, now tends to a normal distribution. Now this is a multi-dimensional normal distribution, so it has some covariance structure with it. Okay, so we have to assume that the covariance structure of this thing converges to something. Right, so it's a little bit more technical, but what you should just think is, okay, so I have some cool distribution that has some constraints on this variety, right? The set of roots in C to the D. And now I'd like to say that the original random variable is normal. It's in this class, basically approximately normal. Okay, so the second result I'd like to advertise today is a result again of Marcus Michelen and myself, where we prove this conjecture. So that indeed these multivariate normal distributions, sorry, these real stable distributions, they're called strong Rayleigh distributions for those who like words, are indeed approximated by multivariate normals. Okay, so here's sort of where we start leading back home in a sense, because we notice here that we have this sigma n tending to infinity, right? And so clearly this can't be some sort of secret consequence of the result I told you before, because we had this extra log n behavior. But it turns out there is a result that's really at the core of this theorem, which we can then lift to imply this. So this result will be for one variable. So let me jump forward here. So what I'm going to tell you now, I think, is independently a very nice result, but it's really the key in proving this multivariate thing. We need to lift this result. Okay, so let's let x be in 0 up to n be a random variable. And now again, let's just write down the roots of my probability generating function. Okay, so I want this behavior of normal just based on the standard deviation going to infinity. So avoiding a ball around 1 is not enough. So what's the right condition? What's the right geometry to guarantee this condition? Oh, I have a question. We have no assumption about the speed of sigma going to infinity. Question retracted. Yeah, so we always need sigma tending to infinity. Yeah, at least. All right. Okay. So here, avoiding a ball around one is not enough, but we need to avoid something else. And here we're going to avoid a sector containing one. So this is like a pizza slice containing one. So for this, let's define delta to be the minimum argument of all these zeta i's. Okay, so what is argument? If you don't know already, it's basically just the distance between this zeta and the positive real axis, right? Just argument in the sense of complex analysis. Okay, I draw a picture if it doesn't make sense. Okay, so just looking now at the minimum argument, so the minimum distance to the positive real line. And we're going to also, in the same way, define our favorite renormalized guy. Then we can prove that this random variable, about which we only know this delta, is close to a normal distribution based only on this delta. Okay, so we have a similar result as we saw before, but now we have no log here. Right, so we can tell how far we are from a normal distribution just from this minimum distance from a root to the positive real axis. Okay, I should say quickly again that this result is sharp in both variables, and it's really sharp in a very strong sense. So if delta is fixed, for example, it's not just that this is sharp, like there exists an example, but every example has to be at distance at least 1 over delta. This is not transparent for exactly the way I've written it here, but in some sense, that's the closest you possibly could get to a normal distribution at that point. Okay. So now let me just to make sure I'm being clear, let me just draw a little doodle here. So there's the complex axis, the complex plane, excuse me. And you give me some random variable and I go and write down the roots of that thing. Okay, so those are the roots of it in the complex plane. Okay, this should be symmetric about this axis, as I've so beautifully drawn. And now I just look at this minimum argument guy. So this is the sort of biggest sector I can draw around the positive real axis that doesn't contain any roots. Right, so if that is delta, this distance gives you some control on the distance to normal. So in particular, if your standard deviation is greater than 1 over delta, you have to be normal-like. Okay.
Julian, we had a couple of questions in the chat about the normalization and the disappearance of the log term.
Is there a reason the log disappears? Yeah, so this is, okay, so the fact that there's no log here is really important. And in some sense, maybe this is the correct generalization of Harper's theorem. There is a reason that the log disappears, but it's hard to see from this point of view. So the existence of this log is not at all trivial, and the fact that it disappears is not trivial. But perhaps I'll be able to say something a bit later. Okay, so the second question is, sigma tends to infinity and the covariance is bounded. How is this possible? Covariance is normalized. Oh yeah, that's true. Yeah, that's a very good point. And there's actually a mistake here, sorry. So I should have also renormalized the covariance matrix appropriately with this random variable. Yeah, thank you very much for that. And that's it, great. Okay, so hopefully that was answered the question. Yeah, thank you for that. Okay, and we have this, great. Okay, so let's just to check in to make sure we all understand the meaning of the theorem again. If we have a sequence of random variables, so I'm writing it in the way that similar to how Pemantle phrased his conjecture, if we have a sequence of random variables and I look at this minimum argument of my roots, if this tends to infinity, then this tends to normal. So it gives exactly sharp condition on this relationship. And this is sharp in both in both parameters. All right, so now I'd like to hopefully say something about the proof of how we start attacking these things. So I have a few minutes. I have 10 minutes here, which is not very much. So I'm going to try to do something a little bit risky, perhaps. So what I'm going to try to do is jump far into the middle of the proof without totally losing you, and try to look around a little bit there to see the kinds of arguments that are going on. So this might be a complete failure, but I'm hoping maybe at least impressionistically to give you some sort of feeling about the flow of things without being too high level. Okay, so here we go. So for the proof, what do we have to do? You give me a random variable, any old random variable, and I get to write down its probability generating function. Okay, so this is some polynomial with positive coefficients. And I get to look at where basically the closest root to the unit circle is. Right, so this means that I have, let's say we're proving the sector result. So I'm assuming I have no roots in some region like this, which I'll call omega. Okay. Obviously, for the ball theorem, that's not the right region. It's something else. So I'm being a little bit general here. Okay, so our goal is to show that this fraction tends to this where z is a normal distribution. That's what we have to do. Okay, so for a reason which I'm not going to explain, it's a very good idea to now look at the log of the absolute value of f of x. So it's not too hard to intuitively justify why this is a good thing to look at, but I'm not going to do it. But rather, I'm just going to say a few good things that happen once we're here. So the first thing is that f of x, that's our original polynomial, has no zeros in our region if and only if this thing is harmonic in this region. So I've done this confusing transformation here, but this is my first justification. Somehow the zero-free property is captured in a nice way. Right? It's encoded in this harmonicness of U. Okay. So here's another nice, I don't know, I wrote it again, but there you go. This guy has actually, if I shove e to the w in here, this guy has a very nice expansion around w equals 0. Okay, so w equals 0 here is, of course, around the point 1. And 1 is very important for us, intuitively from Pemantle's conjecture, but it's also just more generally an important number for us. And what this says is, I'll explain a bit more what these numbers here in a second. This actually is a very nice expansion in this region. Okay, and why is it nice? Is it turns out that these coefficients here aren't just any old confusing coefficients. They're actually familiar numbers. So these AK are renormalized versions of the cumulant sequence of my random variable. Okay, so I don't expect you to know what the cumulant sequence is, but let me point out the two important ones for the moment. The first guy is the mean, and the second guy is minus the variance over 2. And I hope I have this the right way or not 2 times. Okay, someone will write in the chat. But anyway, it's the mean and the variance are the two first guys here. Okay. And the second important observation is it's enough to show, so these magical numbers, the relationship between these numbers actually encode a central limit theorem. So again, I'm not explaining why this is true at all, But if I can show that AK is much smaller than the kth power of the standard deviation, then I will have proved a central limit theorem. Okay, of course, in real life, I need some actual rates here and everything, but this is really the key conflict that's going on. Okay, so I should also say at this point, no math has really happened here. I've just rewritten it in a way which will be favorable for our future endeavors. And in particular, I don't expect you to have any good intuition about this AK. In fact, I think this sequence, given what we know at the moment, just about the roots, is an incredibly mysterious thing. So it's totally unclear at this point why you should be able to prove anything like this. This is sort of mysterious at this point. And in fact, so this is a good start, but I told you I was hopefully jumping up and down a little bit earlier saying positivity. It's incredibly important how the positivity of the coefficients of f come into this. So it's not enough just to consider where the roots are. There's some interaction between positivity of f and the distribution of roots. So on this slide, there's no positivity. I don't see any use of positivity. And a really important idea is to find the right definition to get positivity into the mix. So this definition is not one that is not our own definition. It's in the literature, but okay. But we'll see that using it it's not at all clear either. So let's say that a function on the complex plane is weakly positive if it's always dominated. So if I look at a point z, it's always less than or equal to the sort of corresponding point on the real axis, on the positive real axis. So this is a slightly mysterious, both how to use it, but it's not so hard to show that our function is weakly positive. And indeed, this comes immediately from positive coefficients. Okay, so here's just a little illustration of what positivity is. Okay, so I'm wondering what u of z is, right? Well, how to control that? Well, I just take a walk to the corresponding point on the positive real axis, and I know, and I learn that the value at this point is at least the value at this point. This is not an absolute value, for example. This is just, this is always more positive than this. Okay, so I have to say, we knew this definition for a long time and had no idea how to use it. And a really key, well, for us, what was really important when we came up with this notion of radially decreasing in the paper. So let's say that my function is radially decreasing, which is sort of an extension of this property. So, which says that as I walk away from the real axis, I become less and less positive. So my function decreases along an arc. So here, if I just increase my theta, my u decreases. I walk along a circle. And it turns out that these two properties work really well together. So if, for example, you have no root in a sector, you can prove some sort of weakened version of this property. Okay, so our function is radially decreasing in some neighborhood. Okay, so this is an important piece of the proof, and so I am cognizant of time. So perhaps two more minutes or so to finish it up. Yeah. Okay, so this is a first key aspect, is we can sort of bolster the notion of positivity with the harmonic property to get this stronger notion, or what's actually a bit of a weakened version of what I've written here. Okay. And from this, we get this really key lemma. And this is sort of where all the money is. in this lemma. So we had these very confusing coefficients, which were really genuinely mysterious before. But this lemma allows us to prove that they have some sort of exponential decay at some scale epsilon. So I need a little bit of wiggle room to choose my epsilon to this other epsilon here, which is not quite delta. I need a bit of wiggle. Okay, but it allows us to prove some sort of exponential decay. And you remember that this is quite similar to our goal. Our goal was to prove that I sort of control these AJs in terms of the variance, which is the second term in the sequence. Okay, so that means some sort of decay. Okay, so I was going to sketch a proof of this, which is really the central lemma and indeed a difficult part of the proof. But let me just sort of go above this sketch here, because I do not have time. And let me just jump to a final ingredient here, which is, okay, so that lemma, intuitively, it dealt with the tail. So it said, far enough, these cumulants that are very large, I can deal with in some way. So this boils it down, the problem, to just dealing with some very small cumulants and comparing them to my variance. And here we use a totally different, more sort of combinatorial argument, which shows that we can relate the variance immediately to these AJs, again, relative to some scale which I get to choose. Okay, so I think that's all I'll say about the proof. But once we've shown these things, we can show some sort of uniform bound on these guys, and that sends us on our way to proving a central limit. Okay, so I'll leave you guys today with two of the main theorems and sort of two of the answers to this question that I posed at the beginning of what is the correct generalization of Harper's theorem. So the first is this resolution of Pemantle's question or conjecture. When my roots are bounded away from 1 by some distance delta. So this gives me some absolute control on the distance between x star and a normal, the renormalized thing in the normal. And the second theorem is one that allows us to get rid of this log, right? In some sense, perhaps the correct generalization of Harper, that allows us to show that we have this proximity to a normal distribution if we avoid a sector containing 1. And this is, again, a tight result, and removes this log. And then the other caveat is this also, of course, lifts in some way which I've not explained to prove things about these so-called real stable polynomials and answer this question of Ghosh, Liggett, and Pemantle. Okay, so I think I'll leave it there. Yes, thank you very much for having me.
Julian, thank you for an absolutely lovely talk. So we'll allow people to unmute themselves and ask questions. If you'd like to ask a question, maybe please signal in the chat or raise a hand or something so that we can manage. Maybe I can start off by asking a sort of slightly vague question. So in the case of this first generalization of Harper, so you're essentially avoiding 1 point. Right. So the roots are avoiding a single point, and right. Then in the second sort of multivariate version, you've got this sort of half plane property, or right. Real stability rather. Is it reasonable to hope for other things in the multidimensional case?
Yeah, I think that's, so we actually can prove something a bit stronger in the multidimensional case. So you don't need to yeah, you can avoid some half plane like thing, like some sort of cone or something. But I must admit, it's not a direction I've gone further in. I think that's a really interesting direction to push further. Yeah.
Is it possible that there's some kind of compact set that if you avoid that?
Yeah, I think that's a really interesting question. Yeah, I think I don't know the answer. I don't know the answer to that question, but finding the correct conjecture there, I think would be really interesting for further work. Yeah.
Thank you. Other questions? Thomas, please go ahead, if we can unmute you.
Julian?
Hi there, Thomas.
Hello. Could you please explain why the n to the 1/3 was a natural barrier in all of these other initial results of other people?
Yeah, so basically, right, so this is a good question. So basically, it comes from something like this. So understanding these AKs is quite challenging, but we do know something basic about them, which is we can bound AK by a most n. By reasons, by you sort of fairly easy reasons, we can always bound this by n. So so the first, okay, I shouldn't have said for all k in it. I should have said for all k bigger than 3. So we need that n over sigma to the 3 tends to 0, which gives you greater than n to the 1/3. So basically, they don't have any way of really dealing with these higher cumulants in a subtle way beyond bounding them from above and then asking for a lot of power from this. This is actually something that's kind of interesting about this result to me, and interesting about the proof is that a lot of central limit theorems, basically what you do is you just try to show the variance is big, and then that sort of smashes everything else through. We don't have that luxury here. We really have to do some more subtle relationship between these two parameters. And then that's where you need positivity coming into play and dancing with harmonicity. Yeah. But does that answer your question, Thomas?
I think so, thank you.
Yes.
There's a question from Ewan as well. In the chat.
Oh, I see. So the question is, approximating these generating functions can be a big deal in computer science. Does this approximate normality provide a new method of approximating something? For example, f of 0. That's interesting. That's an interesting question. So f of 0 is like a small ball probability, and this definitely would give you a small ball bound. But so it should be something more in the result. It certainly will give you extremal bounds, but I don't know if so. For approximation, you want something to work always, but then with some margin of error. So I don't know about general. So it will sort of work like. So for example, it will give you f of 0 is at most big O 1 over sigma, for example, times delta. If we look at, whoops, that was a secret result. Rob told me to take that out of my talk because he thought it was a boring corollary. So anyway, yeah, so for example, here it would give you a bound on f of 0 just by plugging in 0 on both sides. In fact, you'll just get 1 over delta sigma. But I don't know if it would give you, of course, say a corresponding lower bound when that lower bound is met. I think that's actually a really interesting question. Thanks for that, Ewan.
Okay, so we should probably stop for a break now. So we'll carry on at 3:30 with the second talk. But before that, let's I'll ask everyone to unmute, and let's give Julian a big round of applause.